Hello, elementary math peoples. This is your pre-recorded lecture for Friday, and we are going to look at some properties and models for the multiplication and division operations. So on Wednesday, we took a look at how to execute some of the standard algorithm thingies with regards to these two operations. And I want to just kind of dial back and take a look, especially at the properties. So we can look at our three big properties, which are associativity, commutativity, and closure. And we're going to see that multiplication is quite nice and division is quite not nice, very similar to addition and subtraction. So let's start, I guess, with, we're going to start with properties. And let's talk multiplication first. Multiplication is always commutative. In other words, it doesn't really matter the order that our two numbers come in. I could do 3 times 4, or I could do 4 times 3, and we're going to end up with the same final product of 12. So remember, that's what it means for an operation to be commutative. The order of those two numbers doesn't matter. Okay, so like I said, specifically we're looking at the order of these two numbers. And the order doesn't matter. The end product is always the same. And this essentially leads us to usually, like I've seen a couple different ways to refer to the numbers in a multiplication statement, but usually we don't particularly care about the two numbers that we're multiplying together. Although it kind of depends. Sometimes I've seen them called the multiplicand and the multiplier, but more often than not, it's easiest just to refer to them as factors. So let's take our 3 times 4 again, just as an example here. We have 3 numbers, right? So our first 2 numbers here, these are called factors. And like I said, it depends on the textbook. Sometimes when modeling is important, if I want to use like the area model or something like that, sometimes it is important for us to attach some specific numbers. But in general, if we're not using a model, I'm typically just going to refer to these as factors because we will look at factors quite a bit inside of Chapter 3 when working a bit more with prime numbers. Now, this number over here, we probably know this one. This one's called the product of our two factors. The reason we only have 2 names and not 3 different names usually is because multiplication is commutative. So it doesn't really matter the order of these first 2 numbers. I can refer to both of them as factors because I know that the order really doesn't matter with regards to these numbers. Now, it turns out that multiplication is always associative as well. And so that means if I have 3 numbers that are all multiplied together, so let's just take maybe 2, 3, and 4. 2, 3, and 4. It shouldn't matter which multiplication I start with. So I could start with 2 times 3, for example. That would give us 6. And then multiplying 6 by 4 would give us 24. If I go the other way and I do the 3 times 4 first, I'm going to get 2 times 12, and 2 times 12 is still 24. So it doesn't really matter which multiplication I start with. If I have 3 in a row, I always end up with the same final product. Okay, so in other words, it doesn't matter if I start with the 2 times 3 or with the 3 times 4. Always end up with 24, which I think is kind of interesting, right? Because our kind of like middle sentence, which is 6 times 4, or like the middle part of our simplification, which is either 6 times 4 or 2 times 12, those numbers always come out to be the same final number. So that's kind of an interesting property for multiplication. Even addition too, right? That these like kind of like middle steps are going to look a little different, but they still end up getting you to the same final product. I think that's really cool. Let's go back to black here, a little AC/DC. Okay, so the set of natural numbers, which is what we've been working with so far, our counting numbers, are closed under multiplication. So what does closure mean again? So just refresh your memory on that. That means if we go into the set of natural numbers and we pick out any 2 of the elements in that set and do the operation, in this case it's multiplying them, I should also end up with a natural number as an end result. Okay, so just maybe a little recall. What we do is we take 2 numbers from the set, now, in this case, the operation is multiplying, so we're going to multiply them. And then we're going to look at the product. We're going to ask ourselves, is the product also a natural number? Is it also from that original set that we started with? And in our case, it doesn't matter which 2 starting numbers we have. The product is always going to be a natural number. So we've seen a couple examples here. The examples certainly don't prove that the set of natural numbers is closed, because I'd have to look at every single possible multiplication, but hopefully you can convince yourselves that this is the case, right? If I start with any 2 natural numbers, so 3 and 6, for example, I could multiply them together. And I'm specifically looking at this product. This is still a natural number. Okay, so remember, I can use the fancy n here to denote natural numbers. That number's still an n, so we're good to go. And this works with, it doesn't really matter how many digits are inside of our number. I'm never going to get like a fraction or a decimal number or a negative number, right? I'm never going to get one of those things when I'm working with the multiplication operation. Now there's one other kind of really nice special property of multiplication that I think is important for us to talk about, and it's a little bit different compared to, say, addition. So this is like kind of a specialized operation or a specialized property that multiplication has. And the property is that multiplication can be distributed over addition and subtraction. So I'll show you what I mean algebraically first, and then I'll show you some examples. So algebraically, the distributive property says the following thing. If I take some kind of number, we're going to call it capital A, and I have like a bracket here, and I have an addition inside of the bracket, like B plus C, for example, then I can actually distribute this multiplication. I can think about this as a multiplication. So we think about this as a multiplication, right? Because it's a number beside a bracket. And I can distribute that multiplication through the brackets to look something like this. So I can actually physically kind of alter this arrangement to get something that looks like A times B plus A times C. Okay, so in other words, if I see something like 3 times 10 plus 2, this is really the same thing as saying I have 3 times 10 plus 3 times 2. Okay, so this is what we mean by distribution. It allows us to work with algebraic expressions in a very, very nice way. So if I, change this, instead of putting a 10 here, maybe I don't know what the base is, and I have something like 3 times x plus 2. Well, I can distribute this 3 through the brackets to get an expression that looks like this. 3 times whatever the base is plus 3 times 2 units. So this is how we think about distribution over addition. And it works the same way with subtraction. If I have something like A times B minus C, it's the same kind of story. I can make this A times B and then subtract A times C. Okay, so it works the same with subtraction as well. And we'll do just maybe one numerical example. We'll do like 3x minus 2. We could change this to 3 times x minus 3 times 2. So that just allows us to kind of expand through the brackets and usually try to simplify some of these algebraic expressions. That's typically where this kind of technique is used. So I would say those are the 4 kind of major properties that I think are good to know for multiplication. Let's turn our focus over now to division. Oh, actually, I apologize. There's one more thing I wanted to talk about. One more property that deals with the identity. So we do have a multiplication identity. So this is new terminology. You would know this as an English phrase, and the English phrase goes like this. Any number multiplied by the number 1 is itself. This is what it means to be the multiplication identity. So I'll just write that in red. And this is probably how I would teach it to my students too, right? Any number times 1 is itself. Okay, so it doesn't really matter what number I start with. If I go A times 1, that's the same thing as A, right? So 5 times 1, that's equal to 5. So that's something that we already know. We've explored already. And so I'm just putting like a mathematical kind of terminology to it and a English phrase associated with it as well. This is kind of an important idea. It allows us to kind of skip through a lot of multiplications that might pop up. So if I'm multiplying by 1, that's nice. And then the other number, of course, being 0. But that doesn't really have a name associated with the multiplication. Or at least I haven't seen one in passing. So that should take care, I think, of the big properties for multiplication. So let's turn our focus to division. Division. I think that's how I spell it. And let's talk about commutativity and associativity. Division is neither of those things. So division is not commutative and division is not associative. So in other words, I should be able to set up a division statement. And let's take one that like divides evenly. So let's take something like 15 divided by 3. We know that 15 divided into 3 equal-sized groups should give us 5 objects in each group, right? $15 divided 3 ways gives each person $5. However, if I switch the order of these things and I do 3 divided by 15, well, that's not equal to 5 anymore, right? This is actually equal to 3/15, or 1/5, right? Which is 0.25, or sorry, 0.2. So there is an interesting relationship between the two final answers that we get, this one and this one. They are inverses of each other, right? They're opposites of each other, thinking in a multiplication kind of way. But these two final answers are not the same. So division is not commutative because the order that the numbers come in is important. Okay, so, just as a little aside here, these are technically what we call inverses or opposites of each other with regards to multiplication. Okay, if I were to multiply these two numbers together, I would get to the identity element, which is 1. And we'll talk about that a little bit more when we get to the fraction section. But this is going to connect back to, I think we looked at this property back here when we looked at the subtraction concepts here. So subtraction, addition is always associative, subtraction is not associative. Maybe look at commutativity. Yes, all right here. So subtraction is never commutative, right? When I switch the order of the subtrahend and the minuend, I get numbers that they look kind of the same, right? We get 2 and -2. So sometimes we call this 2 and -2. Sometimes we call them opposites or inverses of each other with regards to the addition operation. Right? If I added these two integers together, I would get back to the additive identity, which is 0. So kind of a similar thing happening over here. These two numbers are related by being like opposites. And specifically, if we multiply these together, we get to the multiplication identity, which is 1. Now, because the order of numbers is important, we are going to see that division sentences do have 3 different names associated with them. Okay, so let's take a look at the naming of a division statement. Let's see. Yeah, I'm just like quotient. There's the quotient. Even I can't remember what they are. Goodness me. Okay. Do I have them in my notes somewhere? I hope so. Yes. Dividend, divisor, and a quotient. Okay. So these are the phrases that typically go along with a division statement in the textbooks that I've seen. The quotient is the final answer. And then we have these 2 other numbers here, the first being the dividend, and the second being the divisor, so the thing that's dividing into the other number. Okay, so first number we're going to refer to as the dividend, second as the divisor, and the final answer we'll refer to as the quotient. And the reason it has 3 different names associated with the numbers is because division is not commutative. So order is important. It's important to label these differently, unlike multiplication, where we can just call both of those numbers factors because the order is not important. Okay, division is not associative either. So if I were to make up a thing, so let's go 24 divided by 4, that would be 6 divided by 2 should give us some kind of final thing. Okay, so we're going to take a look at this particular order. We're going to go 24, 4, and 2, okay? And we're going to look at doing the first division first, which is 24 divided by 4. That would give us 6. And then 6 divided by 2, that would be 3. So if I do the first division first, I get the final quotient of 3. However, if I try to do this second division first, I get 24 divided by 2. Right, 4 divided by 2 is 2. And then 24 divided into 2 equal groups is 12. So these are not the same final numbers. These are not the same. So the order in which we start our division is important. Okay, so that's kind of the key takeaway here. Again, the order in which we perform our divisions is important. And we'll come back and we'll revisit, like, this idea here is really important for order of operations. So the whole reason why we have to agree on order of operations is because subtraction and division are annoying. They're not associative. I have to be really careful about how I order stuff and write stuff down so that my reader understands how to simplify an expression. So that's why the order of operations is even a thing, because it's important for us to think about how we can start simplifying numbers if there are multiple operations involved. Okay, one other one I want you to know is that when working with the natural numbers are not closed under division. So this means that, well, we saw when working with the standard algorithm, sometimes we can have stuff that's left over that's not easy for us to divide equally into the number of groups that we have. So this essentially lends itself to like decimal numbers or like leftover fractions or things like that. In other words, the quotient that we get may not necessarily be just a whole number portion, okay? So when working on division, I just want you to be aware that the quotient may not necessarily be a natural number. With subtraction, remember that the problem here was that if the second number is larger, when we do the subtraction, we're going to end up with a negative number. So we end up with a number that's inside of the set of integers. With division, it's a different kind of problem. With division, we usually end up with decimal numbers or these partial fractions that are kind of left over. So for example, if we take the number 15 and we try to divide by, I don't know, let's try to divide by 4 instead of 3, right? So a number that's not going to go evenly into 15. And so if we think about kind of how we want to set this model up, we would draw our 4 groups and start trying to put 15 objects in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we have 13, 14, 15. So there's 3 objects that I can't distribute evenly into 4 groups. So we end up getting something like 3 with a remainder of 3. Okay, so if I ever get a remainder that's not 0, that means that we don't have a natural number. 15 divided by 4 is not a natural number. It's 3 point something. It's like 3 point, in this case, I think it's 3.75 if we were to actually do this division on our calculator. So 15 divided by 4 is 3.75. Okay, so a remainder or a decimal portion after our natural number indicates that we don't have closure. Okay, or you can kind of look over here too, and if you get a decimal number after your whole number portion, that means that we don't have closure here. So closure has to work with any 2 numbers that we pick. I have to be able to pick any 2, do the operation, and get a number that's also inside the set. In our case, we found a counterexample. We took the number 15 and 4, divided them, got 3.75. 3.75 is not a natural number. It's actually a rational number. So this is the whole point of working with fractions and decimal numbers, because division is closed under that number set. So we work with integers so that subtraction can be closed. We work with fractions a little bit later in our school career because in that realm, division can now be closed. So in some sense, working with rational numbers, which include all of our integers and all of our fractions and decimal numbers, takes care of most of the problems that we have altogether. Okay? Hopefully that gives you just a little bit of it's more of an aside, like a little backstory as to, why do we have this? Why do we even work with integers? Why do we work with the decimal numbers? Well, because they solve this problem of closure, essentially. Okay, anything else in division that I would like to... There is a nice relationship maybe that I should show you. Actually, let's do that after reading week. I think that's a fun thing to do after reading week. And let's talk just about properties. Talk about models. I think we're kind of in a good spot to talk about the models of multiplication and division. Okay, so in its simplest sense, we can think of multiplication as repeated addition. Okay, so in other words, if I think about 4 plus 4 plus 4, for example, just kind of sticking with our 12 train, I can think about this as 3 copies of 4, which is equal to 12. So this is how multiplication gets connected to the idea of skip counting at some of the younger grades. So those of you that are teaching the younger grades, make sure they're good at skip counting before they go into the next grades, because it's going to be super helpful in letting them kind of tie together this idea of multiplication. So this is why skip counting has a big focus in some of the younger grades. So I would say that's kind of its simplest sense. Now, we can't always use the repeated addition kind of thing, but it definitely works for whole numbers very, very easily. A little bit of a stretch to make it work for integers, and definitely a lot harder of a stretch to make it work for decimal numbers, but kind of possible. So the repeated addition model has like a limited use factor. It's good to start thinking about multiplication, but it's not the best way to think about multiplication. So usually we kind of think about some other models. The most concrete and nice model is as like an area or array model. And even then, I would say this has kind of limited use as well. This is probably limited to mostly elementary school. The idea with the area or the array model is to essentially create copies of one of the factors. So for instance, let's say we wanted to try to motivate y2. Well, let's do 7 times 4. Okay, so 7 times 4 is what, 28? I think, yeah. So let's say we wanted to motivate 7 times 4 is equal to 28. Well, we have a couple different ways to do this. We could go kind of back to the repeated addition, and we could write out 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. We could count up by 4s, right? Skip count by 4s. We can certainly do that to get to 28. The array or area model is going to say, well, let's take 4 objects, 1, 2, 3, 4. So we begin with one of our factors. And then we're going to write out 7 copies of this row. Okay, so there's 2 copies, 3 copies, etc. I think that's 7, 1, 2, 3, 4, 5, 6, 7. Yeah, so here's 7 copies of that original row. So here's the original row. And then the final answer of 28 should be the number of units that I have inside of this kind of rectangular grid. So I could go through, I could now count all of these objects. There should be 28 objects. So this is the idea of the area or the array model. This is typically what we use for the standard algorithm for smaller kinds of multiplications. So I think those are the 2 big kinds of models that we will talk about for multiplication. We've done the standard algorithm, and then what we'll do is we'll come back and we'll recap the standard algorithm after reading week, and we'll do some base 5 questions as well. So that's all I want to kind of chat about with regards to multiplication. So let's turn our attention back to division for a second. This is where things get a little bit more interesting. So there are 2 major types of models for division, and they're going to feel the same with a slight tweak. Okay, so the first main model, or the first main kind of representation, is called the partitive or fair share model. Now, in the fair share model, we view the divisor as the number of groups. And then what we can do is we can fair share the dividend into these groups, and our final answer should be the number of objects that land in each one of these groups. Okay, so the idea with the partitive model, after we've drawn our groups, is to fair share the dividend into the groups, and then our quotient, or our final answer, will be the number of objects in each group. Okay, and then plus potentially some kind of remainder. So let's take a look at, 20 divided by 5. So let's go 20 divided by 5. We know that the final answer here is 4. Okay, so here's how we think through this kind of sentence with the partitive model. I think to myself, I have 20 objects, and I have 5 groups that we need to divide these objects into. So step 1, draw the groups. That was awful. I'm gonna try again. That just looked really gross. Okay, 1, 2, 3. Now let's do 2 groups underneath. 4, 5. So that's step 1. Draw the groups. Step 2. So maybe where should I put the steps? Maybe over here. Maybe I'll do step 1 would be to draw groups. Step 2 is now to fair share the 20 objects. And we can basically do this by just kind of counting. So we're going to count up and get as close as we can to 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. They look like they have faces. 16, 17, 18, 19, and 20. We actually are able to land exactly on 20 objects. Okay, once we've fair shared as best we can, and maybe we have some remainder, the final answer is how many objects are in each group. Okay, so in our case, there are 4 objects in each group. That's our final quotient, okay? So this is what we used when we worked on the standard algorithm for division. So this is used to model the standard algorithm. That's not how I spell algorithm at all. There we go. So that's known as the partitive model. And the second model for division, we're going to do the exact same division sentence of 20 divided by 5 is 4, and we're going to see how to think about it in a different way. So the second way is, let's see, this is called the measurement or the repeated subtraction model. So in this second model, we will, let's see, how did I write it up here? So we view the divisor, yeah. So in this model, what we're going to do is we're going to model the dividend. And we're going to view the divisor as how many things we have to keep subtracting until we can't subtract anymore. So we keep subtracting groups that are equal to the dividend. Keep subtracting groups same size as divisor. Okay, and we keep doing that until we run out of the ability to take anything more away. And then we look at how many times we were able to take away, and that's going to be our quotient. Okay, so let's look at the example here. We'll do 20 divided by 5 is equal to 4. Okay, so again, we're going to think about the number 20 as the number of objects that we have. So we have 20 objects. But now the number 5 is going to be the number of items that we're subtracting, the number of items per group. Okay, so our step 1 is going to change slightly. So step number 1 is now to model the dividend. And we can do this just using small dots. Usually what we would do is maybe use some of the base 10 blocks. But for the purpose of our notes, let's just draw out 20 things. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So you can arrange them in a rectangle, you can arrange them in a blob, it doesn't really matter. So we just want to model 20 objects. So that's step number 1. Step number 2 is to now subtract off groups of 5. Okay, so I'm going to use my red pen here to circle groups of 5 and just start kind of taking them away. So it's kind of like the takeaway model, but we just kind of keep doing it until we can't anymore. So here is a group of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I can make like a T or something here. There's another group of 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, so I keep kind of circling or subtracting or removing groups of 5. However many times I can do this is going to be our final answer. Okay, so and our final answer, so number 3, our quotient is how many subtractions we could do, or how many groups we were able to circle. Okay, so in our case, we were able to make 4 subtractions of size 5, so our final answer here is 4. So hopefully you can kind of see the similarities and differences, right? Like they're very, very similar. Either we think about the divisor as the number of groups, or we think about the divisor as the number of things in each group. That's the subtle difference here in the two models for multiplication. And like I said, I mean, both could be used to model the algorithm, but I find the fair share model a little bit easier for the standard algorithm. The repeated subtraction model can be used. It just usually tends to take a little bit longer because you're always asking, okay, how many times can I subtract this thing? And then it's a little bit harder, I think, to kind of think about that from a modeling kind of perspective, especially with larger sized numbers. So those are your two major models for division. I just want to kind of quickly scan and make sure. Yeah, we'll talk about kind of the division theorem and working with remainders a little bit more after the break. And then, yeah, we'll work on base 5 division after the reading week break as well. So hopefully that gives you just a nice little introduction or a reintroduction to multiplication and division, along with some of the models and some of the terminology that we want to use here in the next couple of lessons. And then, yeah, so after we're finished with multiplication and division, we're going to look at exponentiation, which is kind of our last big kind of operation that we should know for elementary school. And then we'll talk about how that connects to the last number set we'll look at, which is the set of real numbers. So remember, subtraction sucks. Okay, that's where integers come from because the order of the subtraction matters. Division sucks because the order of the division matters. That's where fractions and decimal numbers come from. Exponentiation kind of also sucks. It's good sometimes, but not always. And trying to undo exponentiation is kind of hard. So when we try to undo exponentiation, we run into the last kind of problem in our number system, and that is we may not necessarily get a fraction anymore. And that's where the real numbers come from. They try to solve the problem of undoing exponentiation. Okay, so hopefully that is a nice little recap of some ideas in multiplication and division. Have a lovely reading week. Remember to kind of keep working away at your draft for your lesson plan. I'm going to kind of hopefully finish marking the assessment number 1s for you. Hopefully by the time you've watched this video, you'll have your mark. I'm about half done with those. And if you do have any questions about the draft for the cumulative unit plan, just let me know over the reading week. I will be around most of the days during the reading week, and I'm happy to set up a Zoom call if you want to do some kind of face-to-face stuff, or I'm happy to answer questions via email as well. All right, have a great week, guys. Enjoy some much-needed rest, and I'll see you around the 22nd of February.